Hello, Pratham. Am I audible?
Hello?
Hello. Yeah. Good evening, Pratham. I think I have shared my screen. Is it visible to you?
Yes, sir.
Okay. So I'm starting with the next thing. Okay. Before that, let's discuss what we discussed in the last class. So in last class, if you see, we started with the potential. Okay.
Yes.
Electric potential. What is electric potential? It's basically energy required to take a charge from some infinity to some point. Okay.
Yes.
So what we mentioned that work done by conservative force is nothing but negative of the energy of the system.
Yes.
Clear?
Yes.
Okay. So we are going to continue with the same thing, and this is lecture 11. So what was the formula we have calculated in the last class for potential energy? And right, potential energy is nothing but K Q Q divided by R. Okay. This is the for potential energy formula we calculated in system of two charges, Q at some distance r. Is that clear?
Yes.
If you see, if I made any one of the charge negative, the total energy goes negative. Okay. So if you see, what is the mean by negative energy? Negative energy mean to say a bounded energy. Okay, they don't have energy; they are bounded. They are not free to move enough. But if I make it positive, if you see what I am going to get, if you see what it is a kind of positive energy, right?
Yes.
It means they wanted to go outside. Okay, they want to be enclosed. If you see the structure of atom, what it is positive charge, it is negative charge. Okay, so why these electrons are bounded to these protons? Because the net energy of them is negative. Is that clear?
Yes.
If you have studied the atoms in your grade 11th, you must have noticed that when we calculate the total energy, it comes out to be in the negative format, right?
Yes.
Some negative value comes out. Why? Because this is a bounded energy. Energy, like when it comes out to be negative, means whatever the things you have, that is bounded. Okay, so that's the thing. So I'll just remove this. Okay. So for okay, just let me know if if I remove this charge from here to stabilize this charge at this point, do I need any kind of energy?
No.
No, right? So it means to have energy, I need at least two charges, right? To have
Yes.
electrical energy portion. So I can write single charge don't need energy to stabilize itself. Single point charge, you can say. Single point charge don't need energy to stabilize itself. Okay. So this is the thing. Now what I am going to do is look the way I had this charge, right? What I did, I had Q1, I took Q some test charge Q, I need this much energy. What will happen if I take many charges? System of multiple charges. Then what is going to happen? Look, if I have Q1, okay, if I'm taking some charge Q from infinity to this point at some distance R1, how much energy I needed? K Q1 Q divided by R. Is it clear?
Yes.
Now, in this case, I had another charge Q2. Now, how much energy I needed for to get this charge? Because look, when I take it to this point, what will happen? I needed some energy for this charge at distance R2, for this charge distance R2, right?
Yes.
So another energy will be. So you can say if I have multiple charges at this point, so I can easily say that okay, it will be Q3, Q4, and so on. If distance is R2, R3, R4, what will be the net energy I need? K Q2 Q divided by R2, so on. So I can write it as if you see KQ can be taken as common, KQ common, Q1 plus Q2 dot Q times of n divided by R1, R2 dot R. Is that clear?
Yes.
Okay. So this is the basically system of multiple charges I have taken here.
Okay.
Okay. Now, okay. One more thing. If I ask you what is the unit of it, what is the unit of charge?
Coulomb.
What is the unit of this? Whatever we have written, the energy. What is the unit of this energy? If you see carefully, I have something called K bigger Q divided by R, right? And there is small q. So if you see, can I write this thing? If I say this is one electron, can I write the unit as electron and volt? The whole
Yes.
thing we will call as a volt, okay? This
Okay.
part. So the unit comes out to be electron volt, okay? Although I'm yet to tell you what is volt, so we will discuss this also. That's fine. Now what I'm going to do is, I will calculate the electric potential. I want to calculate electric potential energy because we have already calculated that electric potential. Okay, you can relate it with as you can relate this potential as a electric field and energy as a force, right?
Okay.
What was the difference in electric force and field? Force was basically Q divided by R square. You can't calculate the force of a single charge, right? You need two charges and you can calculate the force between them. But if I tell you what is electric field is nothing but due to this charge Q, if I place at some distance, what will be the intensity? Okay, this is what I can directly calculate. And if I have another charge, if I put it, I can calculate the force as Q times of E. Understood?
Yes.
Okay, so the same thing we are going to do in this case also. Okay, what I'm going to do is I will try to calculate electric potential due to some charge q at distance r. Okay, let's say I'm saying my what is potential comes out to be v at this point. So what is the benefit of this? If I take another charge q here, I don't have to use this formula, k q by r square. Okay, r to calculate energy. What I can directly do? Okay, I will do q times of v. Understood this part?
Okay.
Okay, so let's calculate the v. How? What is the value of v? What it should be the value? You know one thing that the work done by the mm, okay, I'm saying this is point A, this is point B. Okay, you know there's a force in between because two charges are there, right? So can I say that work done by electric force during the displacement from point A to B? So what it will be? It will be nothing but work done of this. It will be nothing but negative change in energy. Is that clear?
So can you repeat?
I am saying I had two charges, okay, and I'm displacing this from point A to point B. Clear?
Okay.
So what my electric force work? You know, when electric force is working, mean to say I'm saying conservative force is working.
Yes.
Clear? So and you know the work done by conservative force is nothing but change in total potential energy.
Yes.
Fine? Okay. What is, just put it like this. Okay. Now what is change in potential energy?
What is changing potential energy?
Yeah. It is nothing but final potential energy, basically point at potential energy at point B minus potential energy point A. Is it?
Yeah. Yes. Yes.
Right? So I'll just write the same thing here, that I have got WAB equals to negative times of UU minus UA. It is energy, right? Let's say I'm saying my this charge was in movement, so I know in this formula this charge is also there. But let's see, I don't know about this part. Okay. Now you need you if you see carefully, this is the energy I needed if I'm taking this much charge, right?
Okay.
If I say for per unit charge how much energy is required, so can I do it? Can I say I can divide the whole equation by Q?
Yeah. Yeah.
Right? Isn't it the same? Like if you know that 10 pence required 10 rupees, so how much
Mhm.
one pen required? Divided by 10,
Yes.
1 rupees. So the same calculation we are doing here. So what it becomes? It is nothing but WAB divided by Q equals to minus UB by Q minus UA by Q. Okay.
Okay.
So what it is not, if you say WAB by Q, it is nothing but work done by electric force in taking charge from a force, work done by electric force per unit charge. Okay, you can write per unit charge also.
Okay.
Electric force per unit charge.
Same
Work
thing.
done by look, the total is work done by electric charge, electric force per unit charge.
Yes.
Per unit charge. From taking A to B, I'm directly writing A to B. Clear? Now, what is this and what is this? If you see, it is nothing but energy at this point, right? Energy at point B. UV is what? Energy at point B. UA is what? Energy of point A. So can I say it is nothing but energy at point per unit charge? And like the whole thing is what? Energy per unit charge. Energy
Yes.
per unit charge. Let the whole thing come out. So can I write this as nothing but negative of some term is there VB minus some term is there VA. Okay, I have replaced this UV. Okay, let's do one thing. Let's write it here. U by Q. Okay, V. Understood? When you
Yes.
write B, it will become V and something. Okay, so the topic of discussion is V. What is V? If you see carefully, WAB divided by Q. It will still be the same. Is that clear?
Okay.
So can I say this V is nothing but potential energy per unit charge?
Yeah.
Because UB was nothing but potential at that point. So potential energy at a point per unit charge.
Okay.
Charge. So if you get idea, I can also calculate potential energy as V into Q.
Yes.
Right? Can I say this?
Yes.
Okay. So whatever you have got the equation, you can see this thing is nothing but work done by electric force per unit charge in moving from A to B, and here V is nothing but potential energy at any point per unit charge. Okay, this is the formula.
Yes.
Okay, now here if you see the formula, I have VB minus VA. Okay, so whatever the formula you have, it is with respect to B or A, right?
Yes.
Let's say I am
Yes.
saying my initial point is infinity.
Hmm.
Now,
Okay.
if let's calculate the work done. Okay, let's calculate potential from taking charge and taking charge from infinity to point B to B. Clear? So you can see I can make this thing as zero because potential at infinity is nothing but zero, right? Or if you
Yes.
don't know this point, we can do this way. What is the potential energy at this point infinity? Because A is nothing but infinity, right?
Okay. Yes.
My A becomes infinity. So can I say W infinity to point B per unit charge is nothing but negative of UB by Q minus U infinity by Q. And this
Yes.
comes as zeros minus UB by Q. So what you can see, if you write this thing is nothing but V. So what is your potential at particular point? Can I say it is nothing but the work done by electric force per unit charge in taking charge from infinity to that particular point? Can you say this?
Yes.
Right? Now I can say that work done by electric force when a unit charge is moved from infinity to particular point B. Is that clear?
Yes.
Earlier, what I was doing, I was saying that work done by electric force in taking a charge and moving a charge from A to B. Now I have replaced this with A, this infinity part. Understood?
Yes.
Okay. So this is what the thing is, and you can also call this VB equals to negative W alpha B divided by Q. Is that clear? Okay. What
Yes.
is the work done by? Okay. What is work done in taking a charge from infinity to B?
So you're asking me?
Yeah, I'm asking. Like in the last class we did now.
Yes.
Okay. So what is
So
that? Let's say,
the
look, work done. We need 2 points to discuss, right? Let's say my work done. I'm saying let's say Q charge are already there. So I took that charge from infinity to this point. Okay, let's say
Okay.
Q is there. Okay, this charge basically I'm taking whatever the here. Okay, so what
Okay.
work done I need to do here? If you see, that is nothing but K Q Q the negative divided by R, isn't it? The distance.
Yes.
This was the
Yes.
work that
Yes.
we had to do, right?
Yes.
Okay, and this comes out nothing but, look, this formula is for work done, but we have another Q also. So you can write it as, so what you have got basically, okay, wait. There's a one negative also, and the one negative from the formula you have come up, so it becomes positive. So what you are going to get, KQ divided by R. Is that clear?
Okay.
Okay, let me go back just in the last lecture. Okay, if you see carefully, I had calculated energy of a man as how much? Look, KQ this by R square, is it?
Where? Yes. Yes. Okay. Yes.
Okay, square should not be there actually. I missed one mistake. The last one was somehow we did mistake. Square should not be there. Okay, it will cancel out in some way. Yeah, when you integrate it, the square will get cancelled. Leave it.
Okay.
Yeah, if you see, I said work done by men is nothing but change in energy. Okay, is nothing but negative of WC, is it?
Yes. Yes.
And the whole thing was equals to K Q and whatever the another divided by R. So R. So the same thing we have applied lecture
Yes.
11.
Yes.
Okay. So you can see this is, I'm still in the lecture. So what you have got formula VB equals to KQ divided by R. Is that clear? So I can also say that potential at some point due to a charge is nothing but KQ divided by R. Basically you have charge. If I ask you what is the potential due to this charge at this distance, you can directly say, okay, that is KQ by R. Is that clear?
Yes. Yes. Sir.
It is very similar to the force. Look, in case of force, what I need another charge also. Like I need charge to calculate force. But if I know electric field, I can directly say, okay, due to this bigger charge, the electric field at this point will be KQ divided by R. Okay, now if you take any random charge Q1, Q2, if you need to calculate force, you can directly do E is equals to Q1, Q2 and something. Okay. Same with the potential also. If I ask you, if I just remove all these charges and if I ask you what is the energy at this point, you will say I don't know. So you can do one thing. You can calculate potential at this point. P.
Okay.
What it is? KQ divided by R. Now if you want energy like potential energy, if you take some other charge and you want to calculate potential energy, how you can do? KQ. I know U is nothing but Q times of V, whatever the charge you are taking. So it becomes Q divided by R. Okay, you have another charge KQ Q2 divided by R. Is that
Oh,
clear?
yes.
Okay. So I'll remove this one. Mm, all right. Can you tell me the unit of the charge? Unit of potential, electric potential.
It was joules per coulomb. Some joules per meter.
You can say joules per coulomb, but in another way,
Coulomb.
because if you see, I am writing a unit of electricity. Look, because now here the charges are there. Okay, consideration should be different also. Okay, look, what is VP? Like potential, it is nothing but
Potential.
this K thing is there, right? Or you can say
Yes.
that, let's remove this. You can say W divided by charge. What is W? W, if you see carefully, what is the, it is nothing but the F dot Tx divided by Q, right? So what is the unit? It is, the force is nothing but, what is the unit of force?
Newton.
Mass. Okay, what is dimension? Just tell me the dimensions.
Of force.
Mass
Wait.
L T minus
Mass.
2. Is it for the
M.
force? Put
Yeah. Yeah.
another L due to this dx divided by charge. What is the dimensional unit of charge?
What do you mean?
Okay, don't know. What is current? Current is nothing but change in charge per unit time. Okay, but I know dimensional unit of current. What is that? A. So this is nothing but, what is for the C? What you have got? A times of, is that clear?
Yes.
Ampere into time. So here also
Mm-hmm.
you can do ampere into time. So what is the
Yeah.
final thing you have got? ML2. This t is in denominator goes upside. It will become minus 3 times. This is the dimensional unit of potential.
Yes, yes.
Clear? And A should be minus 1. It should not be. It should be minus 1. All right, Pratham. So I'm giving you one problem. If you no, let's leave this problem for now. Okay, one problem I'm giving. Maybe if you can solve this. Can you see this problem?
Yes.
Okay, try to solve this one.
10 megawatt energy, megavolt.
Yeah, it is mega electron volt, 10 mega electron volt. Okay.
Okay, okay.
Yeah, one more thing. Look, if the unit is electron itself, that is fine. But if you want to convert one, what is one electron? What is one electron? If you see, one electron is nothing but 1.6 into 10 to the power minus 19
Nice.
coulomb. Okay.
Okay.
So you can convert it in that way also because the QV, right? What is energy? That is QV. So Q is nothing but the final unit of Q is coulomb, right? You can also say coulomb volt
Yes.
or electron volt. Okay, if you write electron volt, you can convert that into coulomb. But in this question, you don't need to convert. You can give it in the form of okay. You need to calculate distance, right?
Okay.
Yeah. So take 2 or 3 minutes and let me know if you're clear with the concept or you need help.
So what was the formula for kinetic energy? Was it half mv square?
Yeah, kinetic energy is simple, half mv square.
Okay. So what was the value of charge?
Hello, Pratham, you are asking for alpha particle, right?
Yeah, yeah.
Are two times of electron.
Uh, okay, okay.
Basically, alpha particle is nothing but helium nucleus. Okay, nucleus of helium. And charge of
Yes, yes.
nucleus is helium, 2 times of proton. The charge is same, so you can call it as 2 times of helium.
Okay.
All right, Pratham, have you solved this one?
Almost. I'm just getting confused how to use the 10 MeV part.
Okay, I'm solving it. Okay, let me know if you have used the same method or something different you have done. Okay.
Okay.
Okay, so look, if in the question, if you see carefully, there is an alpha particle, okay, whose energy is given to us, okay. So
Okay.
you know till when this charge will try to go this point. Like this charge can only move until its velocity reaches to zero. The moment its velocity will reaches to zero, it won't be able to move further, right?
Yes.
So this will be its the closest point I can say, basically
Okay.
in this distance, right? So if I ask you what is the energy of this at this point, let's see what we can do is I know the total energy is conserved, right? So can I do initial energy plus is equals to final energy?
Yes.
So I can say initial energy is nothing but half mv square. Okay. Relatively, I can say potential energy at this point is zero. If I say zero, it will become this. What is the final? I need final potential energy to be zero, like final kinetic to be zero. As I can say, this part is zero. But if it reaches to very close, what will be the potential energy? Let's say this is the distance r, right?
K,
So it will become how much? K
KQ and KR.
q, the smaller q divided by r. Is it
Yes.
clear? So what is the final thing you have got? Mv square is equals to k q by r. Okay. Just put the values. What is half mv square is given to us? 10 10 mega electron directly. Okay.
Acha,
10,
okay. Okay.
okay. Yeah, like because you can see I have given the direct values.
Yeah,
Direct
yeah.
energy is
I
given to.
was getting confused.
And what is the kinetic? This k. K is nothing but 9 into 10 to the power 9 into what is q? The charge is given as how much? 50 times of e.
50
This this is
and
nothing but
2.
alpha particle. It means 2 times of e.
Yes.
Right? So this e and that e becomes e square, and this e will get cancelled out with this one. Divided by what you have to divide. Okay, this is the distance we have to calculate. So
We
take
have
it
to
this side.
find.
Take that r that side. 9 into 10 to the power 9 divided by 50. Okay, 50 into this you can make it as 100. Whole thing divided by 10 into mega. What is this m? 10 to the power. I think it will be 6. Okay, and remaining
Yeah,
is left.
exactly here. I couldn't do this.
Okay, and look, you had two. Okay, we have converted. We had electron, right? You can write that electron as this. If you could remember, I just
Okay.
told you one e is
Okay.
nothing but 1.6 into 10 to the power
Yes,
minus
yes.
1. Okay, look, take it till you can cancel out. So you can see I have cancelled one, but I have rest with one. So I have to do this. Clear?
Okay.
So if you solve this out, you will be getting something like 14. Um, I'm not sure 15 Fermi meter you can say. Okay.
Okay.
Basically, it will be lesser actually. Whatever you are going to get, 14.3 to 5 something. The range will be there.
Okay.
Like basically, you have to do this method. I'm writing that right now.
Yes, yes, yes.
This method you have to do. All right. So look, you are clear with the potential thing, right?
Yes.
Okay. In the next class, what I am going to do teach. Okay, I'll just explain what is equipotential surface.
Okay.
Um, Equipotential surfaces. Equipotential surface. Look, um, the point, or you can say the locus of all points in some region for which electric potential has a constant value is called electro or equipotential surfaces. Um,
Can you repeat?
yeah, I'm just writing the surfaces in which all the points have equal potential. Okay, equal potential is known as equipotential surface. What I meant,
Okay.
let's see. Okay, so I'll just give some example, and the rest part we'll discuss in the next class. Let's say I have this cube surface, okay, and I put a charge inside. What do you think? Will cube act as a equipotential surface? If I put the charge at the very center, what do you think? Will this cube will be acting as an equipotential surface?
Uh, no.
No, right? The reason behind is what is it? It says all the
Because
points
the
on the surface
diagonal.
should have equal potential, right? If I ask you what is the value for formula for the potential due to Q, K Q
Y-
divided by R, right? Let's
Yes.
say if you take this direct top surface, this is let's say this is A, so it is nothing but A by 2 distance, okay. But
Yes.
if you see, if you go at this diagonal point, this and this point is not same, right? So you can see
No.
by moving, if you take this point, this is greater than this length, this is greater than this length, so each point has a different potential, right?
Yes.
So I can say this is not any surface which you can say okay it is a equipotential. Instead, now if I take a sphere, right, you
Okay.
can see if I take any point, this is at distance r, 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 it's an equipotential surface, right? So a sphere, spherical surface can be an example of equipotential surface. Potential surface where charge is at the center. Charge kept at center.
Okay.
Is that clear?
Yes.
One more thing, just some points are there. Equipotential surfaces never cross each other.
What does that mean?
Yeah,
So
equipotential
like
surface. You're
one
you're asking
object.
something?
So you're talking about only one object, right?
No, no. I'm saying I'm not saying about this. I'm saying what is the equipotential surfaces. So I'm writing the characteristics of those. Okay.
Yeah, you said that they never intersect,
Yeah.
right? So the in case of only one, or like if there are many objects.
Yeah, like object in the sense, let's say if you have this as a equipotential surface, okay, if you have another equipotential surface, okay. If let's say, and how you can say, for example, this is my point, I will say this is my equipotential surface, right?
Yes.
If I say I take another circle, do you think it will be an equipotential surface?
No.
Right? Because you can say distance is different.
Yes, yes.
And if I say, okay, if I try to adjust the this surface, this sphere, such that it will be an equipotential surface, it will be like a concentric circle, right? And
Yes.
anyhow it is never going to intersect it. Any, like any two circle, and you can say spheres are not like, they will never intersect each other. Is that clear?
Yes.
So I can say never, otherwise equipotential surfaces never intersect each other. Okay, what will happen if they intersect?
The
The
distance won't
reason,
be equal.
yeah, the distance, actually we can say that at that point there will be two different value of, you can say, electric potential. Understood?
Yes. Yes.
Each other. So I'm not writing the reason.
Okay.
Okay, this second I can say that equipotential surface is always perpendicular to the electric field.
Okay.
You can see the example. Perpendicular surface is this, it is perpendicular to the electric field. Surface is this at this point, basically tangent in the surface, right? This is perpendicular. Tangent here, this is perpendicular, so this is cancelled. And if you take the example of cube, it won't be possible to make a equipotential surface out of that.
Okay.
Surface um, is always perpendicular to electric field. Okay, what can be the third one? If you are moving, okay, what will be the energy, like change in energy in moving a charge on equipotential surface? Change in energy in moving a charge from one point to another, from one point to another, is zero. You know why it is zero? Let's say this, I had a equipotential surface and I wanted to move the charge q from this a point to this point b, and I said it is an equipotential surface. So what is the work done I need to do?
Got it. Got it. Yes.
Got
Yes.
it? It is nothing but this, right? And I told just when vb are same, because it's an equipotential surface,
Yes.
it becomes zero. Clear? So you can say change in energy is also zero.
Yes.
So yeah, this is all for the today's class. If you have any doubt, you can ask, or you can leave the session.
Thank you, sir. Bye, sir.
Goodbye. You can end the session.